For part B, we, we can see that t is multiplied by 2 for the two components. If you compare part A and part B, both have the same function, vector function, but t in B is multiplied by 2. What does that mean? This means that you're gonna get the same curve, the same shape, but different period. Let's recall this idea about the period. The general form for the cosine function is y equal to a cosine of bx plus c plus d. A is the amplitude, b, the coefficient multiplied by x, is the period. Now the period is calculated by 2 pi over b. Since b in this case is 2, this means that b equal to 2, 2 pi over 2 is equal to pi. For the first case, here we have 1. 1, let's calculate the period for part A. The period for part A is 2b, 2 over b, which is 2 pi over 1 equal to 2 pi. Compare the periods of the two. For part A, the period is 2 pi. For part B, the period is pi. So it decreased. If we increase the value, the coefficient over here, the period will decrease. In terms of a real physical system, this means that this one is faster, moving faster. And if we want to visualize this, you have a function as a one wave. Let's take a one wave. This is, let's say or assume that this is 2 pi, the period is 2 pi. For a period of pi, this will be compressed like this. And up. Okay, so it will be compressed to this point. Let's remove this one. It will look like something like this. So it will be the half. The wave will be compressed and will look the same as the first one, the same path, the same curve, but with a decreased value of a period. So for C and D, you can use the online plotter. Please go ahead and try it and change the numbers A, B, C, and D to understand it better. And look at B and note what is happening whenever you change the value of b, whether you decrease when you decrease it or increase it. Check what is happening in your graph. So if this is 2 pi, this is the period 2 pi for part A, it should look like the same but with a smaller one like this. Again, just replace the values for as we did in the first part. Replace the values, calculate and draw. For the third one, we have a three-dimensional vector function. We added a third component, and again, by doing the same thing, replacing multiple values of t and calculate and plotting the first one t equal to 0, start along the x-axis and have 4 units in the x direction. So 1, 2, 3, and 4. The vector starts from here, and as you increase the angle, you're gonna get this kind of curve, very nice one, going in this direction like a spring. This path is called helix. The thing I was talking about about the 2 times t and 1 times t is called reparametrization. So in this case, in the case of reparametrization, you're gonna get the same shape of the curve. You can put any number without changing the shape of the curve, but the period will change. Okay, so let's discuss limits and continuity of a vector valued function. The limit of a vector function as t tends to a is equal to L. Let's assume that this limit is equal to L. In other words, we can write it as such, a very beautiful formula which says that as this is our limit L, and you have this vector function R at this point. This is R. As t tends to a, as the value of t goes closer and closer to a, you will arrive to L. Now, this means that as this number goes to a or tends to a, the difference between R and L becomes smaller and smaller, smaller and smaller until you reach the limit L. That's why the difference between the two is zero as t tends to a.